Thank you. So my name is Piyush Kumar Sharma, and we did this work in collaboration with Mehdi and Claudia. Just a brief word of, okay, I'm not, yeah. Okay, cool. So just a brief word of motivation. Okay. So this field of this talk broadly falls in the field of something called as metadata security, where we assume that the confidentiality of the data has already been assured, but then there are different things about that encrypted data that you can note, which will give you information about the communicating parties based on what level you are looking at. And when we talk about solutions, specifically the network level solutions, in this talk, So I'm talking about a solution called as mixed networks, where the idea is that we want to unlink the fact that some client S is talking to some random server over the internet, where a packet enters the network from the left side, as you can see on the slide. It comes out on the right side by traveling through multiple hops. A packet has to carry forward at least through one of the hops in each of the vertical lines that you see. We call that as a layer. And while traveling through these hops, what mixnets do is they actually mix the packets with other packets that are coming to that hop. And based on how that mixing is done, there are different types of mixnets. In this talk, I'll be focusing on something called as a continuous mixnet, where each packet that enters the system or a particular mix node, it basically experiences a random delay. And this random delay is taken from exponential distribution with the wrong tail. So there will be some packets which will have a very long delay, some packets which will have a very small delay, and some adversary who's trying to analyze who is communicating with whom will have to do analysis for a very long time, maybe try to get to know, see millions of packets before it can make any comment about which communicating parties are involved. And one of the problems with such systems, as you can already imagine, while they provide good anonymity properties, is that they incur high end-to-end latency, which limits the kind of applications that can be supported over such systems. And so we require latency minimization in such systems, which can support wider support of applications. And when we talk about latency in such networks, there are two main components. One is the mixing latency, which, as I was told, that the random delay which a packet undergoes, let's say at a mix hop M1, M2, M3, denoted by mu1, mu2, mu3. But then there's also a propagation delay for a packet to travel from the client to the first hop, second, and eventually to the end server. And while the mixing latency has a fundamental trade-off with the anonymity properties that systems provide, propagation latency do not directly impact the anonymity of these systems. And as a result, previous work has actually looked at reducing the propagation latency. It was presented last year at Ndss. And they provided a set of approaches for the different stages of a mixnet. By stages, I mean this structure that you're seeing that there are 3 hops, 3 nodes in each layer, each having certain connections to each other. So there could be random ways of arranging. There could be some predictive ways of arranging which support certain routing policies. Then you actually define what the routing policies, like which packets can go through which hop, with what probability, and then you also want to ensure certain balancing. But the previous work had certain challenges, particularly the amount of computation that was required for calculating a routing policy with the previous approach. It grows exponentially with the size of the network. And if this network comes any close to size of existing systems such as Tor, it will always be infeasible to calculate the routing policy. Secondly, the previous work only focused on minimizing latency from M1 to M3, which is part of the mixnet. It does not look at minimizing the latency from the client to the mixnet or even from the last hop to the actual destination. And it requires considerable changes to the original mixnet design, which brings me to the point of practical deployment considerations. So when we try to approach this large-scale deployed mixnet called as NIM, like any practical deployment scenario, they were a bit hesitant on such large code-based changes in their network. And so they said that we do want latency minimizations, but we want the system to be lightweight and easy to implement and integrate with minimum code-based changes. Which brings me to the motivation of my work, which is, can we somehow minimize latency in these continuous mixnets while not significantly impacting their existing anonymity properties, keeping in mind that these approaches should be lightweight and easy to integrate in existing deployments. So in order to achieve this, I will walk you through 3 key ideas, where the first idea is the arrangement that you're seeing in mixed node, we assume that we have some random arrangement. It will not contribute to any sort of computation. Then we develop certain routing approaches which do not require the knowledge of the complete network or all the nodes in the network in order to do the routing policy computation. And lastly, we also consider minimizing latency from the client to the first hop of the mixnet. In this talk, I'll be going into the detail of the routing approaches that we created in the interest of time. And in particular, we developed basically 3 routing approaches called as single circle, multiple circles, and regional. And as you'll see, they are very intuitive and in the naming of these approaches. So starting off with single circle approach, it basically consists of 3 steps. First, a client who wants to access network will perform a latency measurement to all mixed nodes that are available. Secondly, the client will form a virtual or a logical circle with a radius r, where r defines the latency bound that the client wants to have for its latency. So it could be a value such as, let's say, 300 milliseconds. And now in this logical circle, whichever nodes basically fall beneath the circle, a client will be selecting a path among these nodes. And as you can imagine, this is not the whole set of nodes. This is a part or subset of all the nodes that are available globally. So the routing computation is quite minimized. But you can also imagine that even within this circle, there might be different ways of selecting these nodes. And so there are multiple ways of creating a path. In order to ensure that there is certain amount of anonymity always there in the system, we basically enforce a constraint that minimum alpha percentage of the nodes always have to be part of the circle that the client is selecting. So if it selects a very low latency configurations, let's say 1 millisecond, and there's maybe, let's say, just 3 hops, it cannot do it because you want a constraint by the alpha percentage of mixed nodes. So let's look at a bit more pictorially. So let's say these are a set of mixed nodes that are available on the globe. And let's say there is a client. It wants to use this network. So as a first step, it will actually create a logical circle around it. It will do the measurements. It will say a latency R is what I want to have for my paths. And in this case, you can see that there are 4 nodes that fall within the circle. So once this step is done, as I told about that in mixnets, there are different layers. So in this, like the blue node represents the first layer, the yellow the second layer, and the green the third layer. Since there are only 4 nodes, so it will be selecting its paths from among these 4 nodes, where it has a choice to select between M2 and M3, M1 and M2 in the first layer. But in the second and third layer, it has no choice. But in a realistic setting, there will be much more nodes and with much more combinations that the client can do for. And as you can imagine, that this is very simple. The client just has to do latency measurements, form this circle, and it will be able to do this routing policy computation. Which brings me to the second routing approach. As you can imagine in the single circle, that while some latency nodes could be closer in latency to the clients, they might still be far away from each other. So it does not capture such corner cases. And you can see in this diagram, M2 to M6, while it falls in the circle, incurs more delay in comparison if you would have selected M5. So multiple circle is an improvement over the single circle approach, where the client creates multiple circles. So the first circle that the client creates, it's only used to select the first hop of the mixnet. Then once that first hop is selected, another logical circle is created, which selects another hop for the second hop. And then similarly, we select the third hop among these cases. As you can imagine, this is slightly better in latency optimization as it goes away from those corner cases, but it requires a little more computation and little more knowledge, in the sense that now client also needs to know what is the latency from mixed nodes in first layer to all the mixed nodes in second layer, and similarly from second layer to third layer. So that basically adds on the computation. Which brings me to the last approach, which is a very simple approach called as regional mixnets, where our idea is to not have one complete big global mixnet, but small regional mixnets. There could be multiple ways of dividing a mixnet based on region, maybe client density, maybe the density of the mixed nodes that are there. We selected in this case for evaluation, a geographical distribution because it's much easier to control. Any sort of, dynamic, logic such as client density or mixed node will basically require a lot of changes at multiple instances in the design. But as you can see here, the client has to do nothing. It just has to select which mixnet it wants to select for its routing, and it does not need to do any sort of calculation. So these are the three routing approaches, and till now we have established that we wanted to minimize latency. We have looked at these three routing approaches, and it brings me to the evaluation, where, as you can imagine, we are interested in two main parameters. One, what is the latency in the default system, and once we use our approaches. Corresponding to those latency minimizations, what sorts of anonymity we are getting. So we quantify anonymity by a concept called as entropy, and just to give you a sense, higher the entropy in the system, the more the anonymity, and lower the entropy in the system, the lower the anonymity that we assume. I'm not going into the details of how exactly we do these calculations, but just to give you a sense of how anonymity is evaluated. And then we also calculate the trade-off, which gives us a good sense of if we want to take this in the network or not. There are certain variables for our approaches. So as I mentioned, that routing within the circle can be done in multiple ways. A client can randomly select these hops. A client can actually select these hops proportional to the latency, or the client can actually use the previous work's routing called as the Larmix routing. And then there's obviously the alpha, like the minimum number of mixed nodes that you always want to have in the network. And there are various experiments that we conducted. In this talk, I'll be going into the detail of two major experiments, latency with respect to the radius of the circle, and entropy, which is anonymity with respect to the radius of the circle. Just to give you some idea of the data set we use, so we partnered with NIM Network, and we got the actual mixed node latency data set. And we can be sure that these latency measurements are actual measurements because it uses something called as Verloc, which makes sure that these latency measurements that are conducted are authentic and can be actually used for evaluation. Which brings me to the result. I'll talk about the results of multiple circle, where on the x-axis, you can see that we have the radius of the circle. And for each value of the radius of the circle, we basically plot the value of entropy. As you can see that increasing the radius of the circle from close to 2 milliseconds to actually 50 milliseconds leads to a rise in entropy, which is supposed to be accepted because more the size of the circle, more the number of mixed nodes, and more the anonymity that you should have. Correspondingly, when we talk about latency, it also increases naturally. So when we increase the size of the circle, we can see that overall the trend is increasing. But even in this increasing trend, you can see that some approaches are performing better and some are not performing that better. So particularly uniform routing or random routing, you can see it has the highest entropy. It's at the top on the graph on the left. But it also incurs higher latency. So when we talk about trade-off, it's not that good. Same goes for the approach, which is at the bottom on the blue. But the proportional approach overall does better with respect to trade-offs from our experiments, where you can see that the green line in the entropy, it has slight reduction in anonymity, but you can see that its latency is quite minimized in comparison to the random case. Similarly, I'd like to talk one more result about the regional mixnets, where we divided the whole internet into two sets, the EU mixnet and the North America mixnet, because that is where most of our actual mixnet nodes were. And as you can see that with the increasing value of randomness in the network, we are having higher entropy, and it also leads to higher latency. But overall, when we talk about the trade-offs, the EU mixnet with EU clients gives the best possible trade-off with respect to anonymity and latency. So to summarize and give you an overall broad picture of these, so as you can see in this table, so vanilla is the default setting, like that is there in the mixnets. Larmix was the previous work, and single, multiple, and regional are what we developed. As you can see, that the latency in the vanilla mixnet is the highest, but I'd like you to focus on the trade-offs column, where you can see that when we talk about the vanilla mixnet or Larmix or single circle, they are having certain trade-off with respect to how much entropy they are getting for latency in the network. And we can see that the multiple circles and the regional mixnet really make that trade-off much higher, making these approaches much more suitable for deployment and for actual latency minimizations. So to summarize, in this work, I talked about LAMP, which is an approach to minimize latency in mixed networks, where we, among other things, developed 3 novel routing approaches. We performed a realistic evaluation on the deployed mixnet name, where we obtained superior trade-offs than the state of the art. In particular, we basically had 3 times better latency and anonymity trade-off than previous work. While I haven't presented in this talk, but we also conduct a thorough theoretical analysis arguing about how much complexity or how much latency these approaches will incur if they are actually deployed in real and the network scale to the size of Tor or even beyond. And we also conducted a thorough security analysis in order to understand if some set of the nodes are corrupted by themselves, what could go wrong, what kind of fraction of corrupted paths could be here. And the bottom line is that LAMP does not give away any significant advantage. I would like to make a note that all the graphs and all the results that I talked about in this talk or in the paper, we got all the 3 batches, so you can actually scan the QR code, see that code, and you can actually reproduce the results that I'm talking about here. So yeah, thank you so much for listening, and with that, I would like to conclude my talk.
So any questions for this paper? Okay, sounds good. So even I don't have any questions for this paper. Okay, thank you.
Sure.